Okay, so we have yet another chapter to talk about today. But before I launch into that, let me ask, what questions do you have about anything?
How long is the exam going to be open for?
I will open it tomorrow morning, and let me find, where's my folder? Exam 3. Monday night at midnight. So from
Does that
Wednesday.
mean we're having lecture tomorrow? Since our test date would be tomorrow.
Correct. Yeah. So there's no lecture tomorrow, and in fact, my life has conspired such that I will not have office hours tomorrow either. So I know for the other exams I've had extended office hours. For this one, I'm actually not. But I think we've got a little extra time for this exam. Wednesday to Monday is longer than usual, so I'm trying to make up for that.
Hi, I have a question too.
Yeah, sure.
About the exam tomorrow, I'm not sure if you already mentioned this in prior exams, but are we allowed to have multiple equation sheets like those open?
Yes. So there's the equation sheet for exam 3, which should be most helpful, but
Okay.
you can use 1 and 2 if you want.
Okay, awesome. Thank you so much.
You bet. Also, extra for this exam is a table of planetary data. It'll be the last page of the, no, it won't, because it'll be a file attachment. It'll be a JPEG, I think. But if you look at the practice exam, the very last page is a table with masses and distances to various celestial bodies. You'll have that available as well. Other questions?
What do you want us to write for the lab 7 write-up conclusion?
More or less, no, not more or less. I mean, you're comparing a theoretical moment of inertia to a experimentally calculated moment of inertia. So compare them, right? You should have several experimental values you can take as standard deviation so that you can you have an error range. Does that make sense?
Yeah.
There is an error in the analysis of that I identified maybe 15 minutes ago. So I will send that out. Maybe I'll send it out to everybody. Basically, the calculation for torque is a little wrong. But what I'll do is I'll make a small video about it and I'll post that.
Okay. Thank you.
You bet. Anything else? Cool. Okay. So we've been talking about thermal physics. So let me do this. There. So we started and ended chapter 10 yesterday. And in chapter 10, I can do better than that. Let's see, I introduced the idea of temperature, right? Thermal expansion. The atomic model of matter, which gave us things like relating the thermal energy of a system to the number of things in the system and its temperature. Let's see, and the ideal gas law, right? So PV equals NKT or nRT. And I am aware that I didn't do a whole lot with the ideal gas law as far as examples go, but I did do several of them in the chapter 11 stuff, which you should have watched for today. So you should have seen some examples of the ideal gas law there. So let's recap chapter 11 basically, and I'll talk about these ideas. So Chapter 11 starts with specific heat. Specific, yeah. So specific heat is relating the heat added to a system and the change in its temperature. Now, this is kind of distinct from this equation here, and it's also kind of similar, right? Because we've already said, well, if you change the thermal energy of a system, so we'd said delta E thermal leads to a delta temperature, and you can change the thermal energy of a system by adding or taking away heat. Heat here is this variable Q, right? Yeah, you can change the thermal energy of a system by adding heat. You can also change the thermal energy of a system by doing work on it, and we'll see that in chapter 12. Actually, the first couple of videos for chapter 12 are already uploaded. Those are for Thursday. In case you're confused by the fact that I'm actually a day ahead. I'm a day ahead. Okay. Specific heat, though, is useful for solids. You can also do this for gases, but it depends on whether how you're changing the heat, or sorry, how are you changing the temperature? Because you can change the temperature and also change the pressure, or you can change the temperature and also change the volume, and that's related to the ideal gas law. But for like a solid or a liquid, we treat it like the volume is fixed, and basically the pressure is fixed as well. Okay, so specific heat. When we add heat to a system, we get a temperature change that's related to the mass of the system, and this letter C. The letter C is the specific heat. All right. Yeah, this is fine. And again, this kind of makes sense. Specific heat is an intrinsic property, right? So there's a specific heat for water. There's a specific heat for metals, for various liquids. In fact, if you look at the lecture handout, there are several of those there. Chapter 11. So specific heats for some materials is this table over here. Clearly, I use some of them in the lecture and the pre-lecture videos. So let me talk about, because I did an example of this in the pre-lecture videos, where I talked about an alligator absorbing energy from the sun and changing his temperature over some time. Let me again mention the distinction between specific heat and heat capacity. Heat capacity is the mass and specific heat together. So there's the heat capacity of some material is the amount of energy I have to add to that specific chunk of material to change its temperature by a degree, whereas specific heat is the amount of energy I have to add to a kilogram of a material to change its temperature by a degree. So specific heat is a little more useful generally. Heat capacity has to do with, like if I have a sample in my hand, I can talk about the heat capacity of that actual chunk of material. Let's see. Oh, let's talk about units for heat. So heat is an energy, right? So the unit for heat is a joule. Right, so heat is just thermal energy, but it's still just energy. But there's another unit that we often use, which is the calorie. And the calorie is the energy that it takes to raise the temperature of a gram of water by a degree Celsius, I think. And that's distinct from a calorie, which is capitalized. That calorie is a food calorie. and that is 1,000 little calories. All right, and that just has to do with what unit makes sense for that, right? So when you have, I don't know, say a glass of Mountain Dew, this actually has no calories because it's diet, but let's say if it did, you know, if we're giving that unit in lowercase calories, which is the energy it takes to raise the temperature of 1 gram of water 1 degree, it would be a very, very large number, which is like, it's not crazy, it's just inconvenient. All right, questions so far? Okay. So what else can we do? Well, when we add heat to a sample or take heat away from a sample, changing its temperature is not the only thing that can happen, right? We can also change the state of that material. And again, I introduced this in the video, but this is heat of transformation. Heat of transformation of a material. And this is just, so Q equals M times L. All right, when you transform a material from, say, a solid to a liquid, or vice versa, the heat does not go into changing the temperature. It goes into breaking or making atomic bonds. All right, so let's say we're talking about turning a solid into a liquid, right? So what does a solid look like? Well, we've kind of modeled it as atoms or molecules connected by springs, right? So if I add some heat to this system, so let's add Q, I could get to a liquid. So what does a liquid look like? I don't know. They're now loosely bound, right? But they're not rigidly bound like they were before. So what did that heat do? It went into breaking those bonds, right? You had to pull the atoms apart somehow. So the energy, instead of going into kinetic energy, it went into the work that it takes to pull those apart. Okay, so that's why there's not a delta T on this. Let's see. For the solid to liquid transition, we use the heat of fusion, and for the liquid to gas transition, we use the heat of vaporization. And as I mentioned in the video, you have to put the sign in manually. All right, because for heat capacity, very specific heat, the delta T, how many colors do I have here? The delta T tells me the sign, right? So Q is generally heat added. And so if Q is negative, that's actually heat that's taken away, right? So negative added is actually taken away. So if delta T is negative, I have to take heat away. There's no automatic sign for the heat of transformation, so we have to put the sign in manually. Let's see. Kind of the not the trickiest thing, but a common thing to do with this is to think about taking a sample from one state to another state. I did an example in the handout. Let's do this one. Let's say I've got, I don't know, I'm just gonna make up numbers, 35 grams of ice at -5 degrees Celsius. And let's say I want to completely boil it away. I think I'm missing an E in that, but I didn't major in spelling. So I could ask, how much heat do I have to add? So how much Q, question mark. So we're not going to do this mathematically, like I'm not going to plug all the numbers in. I just want to talk about step by step, what do I need to do here? So we're starting with cold ice, right? So the first thing I have to do is heat the ice up to its melting temperature, right? I can't melt -5-degree ice because when I add heat to that, it's going to change its temperature. So we could say Q1, bring ice from -5 degrees to 0 degrees. And then I can add more heat to melt the ice. So when I melt that ice, I go from 0-degree ice to 0-degree water, right? Again, and the phase change, the temperature doesn't change, just the state changes. So I continue to add heat, and that will bring the melted ice from 0 degrees C to 100 degrees C. And I continue to add heat. And once I'm at 100 degrees C, then I can boil the melted ice. So to calculate the heat needed to completely boil away cold ice, I need 4 terms. Does that make sense, you guys? Two of these are MC delta T terms. So this one is an MC delta T. And that C is a heat capacity. That's the heat capacity. That's C for ice, right? And you can look that up. Let's see. There. The heat capacity for ice is 2090. Let's make the stuff go away. Just so I can put another circle there. The heat capacity for ice is 2090 joules per kilogram Kelvin. And the heat capacity for water down here is 4,186. The reason those are so different is that when you add energy to ice, all it can do is jiggle a little more, right? So the water molecules are bound to each other, but they can't rotate. But once you add energy to water, like liquid water, it can not only add to the translational kinetic energy, but also adds to the rotational kinetic energy. But when you add to rotation, that doesn't increase temperature. It increases total energy, but it doesn't increase temperature because temperature is related to average kinetic energy, like translational kinetic energy. So again, that's why you have to add more heat to liquid water to get it to increase its temperature than you do solid water. Okay. Yeah, that's probably good for that. So let's finish this conceptual example here. So we had the one MC delta T term. Here's the other MC delta T term. Now that C is C for water, even though it started as ice, right? Now it's no longer ice. That's why I call it melted ice. You could just call it water, but I call it melted ice to remind myself that the mass here is still the original mass of ice. So if I were going to call this mice, right, the mass of ice, this would still be the mass of ice, even though it's water now. And these other two terms are ML terms. This is an ML. This is the heat of fusion, right? Since we're at the solid liquid boundary, and this is the heat of vaporization since we're at the liquid gas boundary. Okay. Do you guys feel confident that you could plug into this and figure out exactly how much energy it would take to boil this completely away?
Yeah.
Okay, Megan feels good, and that's good enough for me. So, so great. What else could we do with this? Well, what if we wanted to do this in a very specific way? What if I said, I want to add a hot aluminum cube to, so let's take this ice cube let's put this ice cube in a thermos. I used to have a Teenage Mutant Ninja Turtles thermos when I was a kid. So let's put it in that thermos. So there's our ice cube at -5 degrees Celsius. And let's say I want to put an aluminum cube. So what color is aluminum? Perfect. There's my aluminum cube. Need a fill function here. It's not Microsoft Paint, but so I could ask, if I know the mass of this aluminum, what is the initial temperature of this aluminum that if I put it in there with this ice cube, it would exactly boil away all of that ice? Does that make sense? It's not hard to imagine. If I just put like a piping hot, like a super, super hot piece of aluminum in there, I could boil away the ice cube. But it would also heat up the steam, right? I want to know exactly how hot, exactly what temperature does this chunk of aluminum need to be to make this happen. So what I'm introducing here, again, if you watch the pre-lecture videos, I'm introducing the idea of calorimetry. Right, so I just figured out exactly the amount of heat that I need to boil this completely. Right, that's Q1 plus Q2 plus Q3 plus Q4. So if I wanted to know what initial temperature this needed to be, I could add Q5, and Q5 would be cool, that's not how you spell cool, there, cool aluminum cube to the equilibrium temperature, right? And I could set that equal to 0. Again, because if this is a thermally isolated system, right, and that's what a thermos is intended to be, is walls that don't allow heat to go in. So there's Q bouncing off, because that's totally physical. No, let's make that go away. So this sort of math would let us do that. So I'm not describing calorimetry in super detail right now. I'm just kind of segueing into it. Again, I'm assuming that you watched the pre-lecture video about this. Are there questions about calorimetry? The like prototypical calorimetry question, like the most basic calorimetry question, is to say, let's let two samples of something come into contact with each other and ask what temperature does the entire system come to. So I've kind of drawn this already before, but again, let's put it in an isolated chamber. Then this could just be a styrofoam box. When we do calorimetry labs in person, you just use styrofoam, and styrofoam works really well for this. Okay, so again, I could just have, let's say, a chunk of hot metal and a different chunk of cold metal. They could be different kinds of metal, right? One could be gold and the other could be silver. And what we're going to have is heat goes from one to the other. So all of the heat lost by, let's call this guy sample 1, is gained by sample 2. And heat transfers until the whole system gets to an equilibrium temperature. And again, we just say Q1 is the heat lost by 1, Q2 is the heat gained by the other. They have to equal each other, so we set it equal to 0. 1 is positive and 1 is negative. Okay, so take a look at that video if you haven't, and that should, it gives you an example of this sort of thing. Okay. So there's one other idea in this chapter, which is heat transfer. And you may notice I'm not doing specific examples. That's because there were only, I think, 6 examples in this lecture handout, and I worked 5 of them in the pre-lecture videos, with the exception of, I think, example number 2, but that's okay. So heat transfer, there are 3 ways to transfer heat, or 3 ways we'll talk about in this course. There's conduction, convection, and radiation. And as I am apt to say, I did introduce all three of these in the pre-lecture video. And I worked an example for two of them. Very briefly, conduction is heat transfer through a material, right? So you're conducting heat atom to atom. And the expression we had for this, when we talk about heat transfer, we're calculating a transfer rate. So it's heat transferred per unit time. And for conduction, it's a thermal conductivity, which is that letter K, times, let's see, cross-sectional area divided by a length and times the temperature change, or the temperature at either end of that material. So we're basically saying, if we have a rod here and we've got T hot on this side and T cold on this side, heat is going to transfer through this from hot to cold, right? So I'm going to get Q going this way, and the rate at which that transfers is proportional to these things, right? The thermal conductivity, the cross-sectional area, the length here, and the temperature difference. So let me ask you this. On a cold winter morning, when you get out of bed and you're barefoot, you may notice a difference between the linoleum, the way the linoleum in your kitchen feels, to the way the carpet in the living room feels, right? They feel like like one is colder than the other, right? Is that because they're literally at different temperatures? Probably not. It could be. You could imagine a situation where they would be different temperatures, but if they're sitting right next to each other, right, you take one step and you go from carpet to linoleum, right, or maybe hardwood, but for me it's linoleum. It feels like it's colder. It's not, though, because they're in thermal equilibrium, right? We just talked about when two things are in thermal contact, they come to equilibrium. The reason they feel different is because they have different heat capacities. Sorry, that's similar to heat capacity. They have different thermal conductivities, right? What's in the carpet? Well, carpet contains a lot of air, and air is a poor conductor of heat. Again, you can look at the lecture handout and see here. Thermal conductivities, yeah. Oh, wow. Here. Air is a terrible conductor of heat, whereas linoleum, what is linoleum? I don't know. It's a non-metal, something like this, right? At best, it's 10 times bigger. At worst, it could be 100 times bigger than the thermal conductivity of air. So we need to be careful when we say, oh, this feels colder than that. Well, it may not actually be because they're different temperatures. Or better said, there's just more to it than that. Okay. So convection. Convection is heat transfer by moving the actual hot thing, right? So instead of transferring energy from atom to atom, you just move the hot atoms from one place to another. That feels like cheating, but it's not. It's just another way to transfer heat, right? So we don't do any math associated with that. I did mention that convection, so conduction through air is terrible, but convection via air is actually great because air is easy to move, right? Questions so far? Cool. So let's talk about this last one. The last item here is radiation. And radiation is energy conducted away, not conducted, transferred to or from an object by light. All right. So sometimes we call this, well, no. This is related to thermal radiation. Sometimes we call it thermal radiation. Thermal radiation is just light that something emits because of its temperature. All right, so if you have ever heard the expression white hot, right? Or you've seen coals in a campfire, right? So the light from a campfire comes from two things. One is from an actual chemical reaction, right? Combustion of fuel with oxygen. But the other thing is when the outside of that is burned, you have a core that is just hot, right? It's still combusting somewhat, but it's not flames, right? So the light that comes from the coals in a fire is just because it's hot. Same thing as if you heat up, if you have an old-fashioned light bulb, right? So we have lots of light bulbs now. We have compact fluorescent, we have LED, but old-timey light bulbs, right? Or the ones you can buy at the dollar store, have a filament, right? And a filament is just, it's just wire, right? And when you run electricity through it, it gets hot. And when it gets hot, it emits light. That's exactly, we're taking advantage of thermal radiation. The fact that when something is hot, when anything gets hot, it gives off light. Okay, and if you feel like, let's see, if you feel near this light bulb, right, it really is hot. Not just because the glass is hot, because it's near the filament, but it's actually giving off light, and the light is warm as well. So the power or the heat conducted away by radiation is related to E, which is the emissivity of that surface. It's a number generally between 0 and 1. Has to do with how much light reflects off of it and how much light it absorbs. Sigma, which is a constant. A, which is the surface area, and temperature to the fourth. So that temperature has to be in Kelvin. And that fourth power means that this is really sensitive to temperature, right? So a small temperature change results in a big power output change. The other thing we notice here that I'm not talking about in this chapter is the color of the light changes as well. So the color is proportional just to T to the first power, but that's why things that are just warm tend to be red, right? In fact, things that are like the surface of your body, right? Your skin temperature is high enough to emit infrared light, and as things get warmer and warmer, they give off red visible light. Warmer and warmer still, they'll give off light that's more spread out in the visible. So that would be distributed throughout the entire visible, and that's why something that's really hot is white hot, because it's giving off all visible light, not just red. Okay, so let's do an example. I actually do want to talk about an example today. I've got about 5 minutes, which is perfect. Let me pause though. Do you guys have any questions? Cool. Okay, so example number 6 says a small spherical glass bead having a radius of 1.5 millimeters is removed from a blast furnace at a temperature of 195 degrees Celsius and placed in a room temperature environment, right, 27 degrees Celsius. The net amount of heat radiated from the bead in the first 5 seconds after removing it is 86 millijoules. What is the emissivity of the bead? So we are looking for E. Again, E has to do with what fraction of light that hits this surface is absorbed and what fraction is reflected. An emissivity of 1 means it absorbs all of the light that hits it. Okay. So we have to think about what's happening here. Well, we pulled this bead. So a bead is like a sphere. It is a sphere. And we pulled this bead out of a furnace that was at 195 degrees Celsius. So that's the temperature of this. And before we do any math with it, we're going to have to convert it to Kelvin. So it's emitting some thermal radiation. What color should that be? Red, sure. And we could calculate, if we knew the emissivity of this thing, we could calculate what that is, right? But it's also absorbing light at the same time, right? So imagine this. What's going to happen to this bead? Well, it's going to emit light. It's going to radiate heat away. But even if it were in a vacuum, right? Especially if you're in a vacuum, all it could do is radiate heat away. But it's not going to radiate heat away until the temperature is 0, right? It's not going to radiate to absolute 0. It'll radiate until it's radiating heat at the same rate as it's absorbing heat from its environment, right? And that's why this doesn't cool. Again, it doesn't cool to absolute 0. It cools to an equilibrium temperature with its environment. So at the same time, it's absorbing some heat from the whatever's around it. And the things that are around it are at this 27 degrees Celsius. So I could talk about power. This is power. The net power absorbed or emitted by this thing is going to be P emitted minus P absorbed. And again, power is for this, it's Q over delta T, delta little t. It's E sigma cross-sectional area times T to the 4th. So I can put these two together. One of them is for the temperature of the object, and the other is the temperature of the environment. So let me fill this out. E sigma A T of the object. What do I want to say that? We'll say T of the bead to the 4th minus E sigma A T of the, give me just a second, T of the room to the 4th. Okay. So what do I have? I know sigma is just a constant. A is the the surface area. The temperature of the bead is a thing I know. The temperature of the room is a thing I know. E is what I'm looking for. So do I know P net? Well, I do, right? P net here, let me erase some stuff so I have some room to write it. P net was given to me. It was 86 millijoules in the first 5 seconds. So I can calculate there's a number for that, right? What does that turn out to be? I didn't calculate. No, I didn't. It's 86 times 10 to the minus 3 joules divided by 5. It's 0.0172 joules per second. And that's going to equal the emissivity times sigma times A times T of the bead to the 4th minus T of the room to the 4th. So I'm going to leave plugging numbers in for those for you, right? I think you can do that. Again, the temperatures need to be in Kelvin. The area is a surface area. What's the surface area of a sphere? Anybody? It's related to, it's got a pi in it for sure.
2 pi r.
There's an r in it, but if it's an area, the r is going to be squared. But that's not quite it either, because pi r squared is the area of a circle, but this is a sphere.
Is it 4 pi r squared?
It's 4 pi r squared. So how would you remember that? You can just look it up. Google. I've got a Google Home in every room in my house so that Google knows everything that I do. But if you can remember the volume and take a derivative with respect to r, the derivative of volume gives you surface area. That's how I remember the surface area equation. In case you're ever on a desert island and need to know. Anyway, again, sigma is the number that we know. So we can use this to solve for the emissivity. Turns out to be 0.27. Okay. I will ask one more time and then we'll call it good. Okay, are there any questions? Cool. Okay, well, so that begins and concludes chapter 11. So you've heard me talk a lot. You've hopefully watched the pre-lecture videos. So the next step is to practice, and that would be the discussion problems. So that's what's up next is discussion tonight and tomorrow, depending on which section you're in, is problems for chapters 10 and 11 together because the material is pretty similar, different, but similar. So we will do that, now. So thank you for your attention, and I will see you guys in discussion.